Good morning, everyone. I hope you enjoyed the dinner last night and made it home on time. So very good to see, I think, almost everyone back for this first morning session. We'll have Ed presenting on visualization with Meshalyzer, which is a very powerful tool and very much tailored to the openCARP data formats and types of visualizations you want to do. So yeah, thank you, Ed, for presenting this tool.
All right, thanks. So I'll be talking today about visualization, about using Meshalyzer, and a little bit about data manipulation. If anyone has, any, feel free to interrupt me if you have any questions. There's a diverse crowd here, and I know even though I wrote a manual for Meshalyzer that documents everything, I also know no one ever reads it. And so there's a lot of things, and you'll say, oh, I didn't know I could do that. Yeah, I can do that. So yeah, so Meshalyzer continues to advance. Again, it's my own little side project, so whenever I need something, I just implement it. So today I'm going to show some more features, talk about some data manipulation. So one of the things that I want to talk about is Igb Format. That's the, I would say proprietary, but we've been using it in openCARP and CARP for a long time. Started actually at University of Montreal a long time ago. So some of these things you do now are going to stick with you the rest of your life. Be prepared. So there's a bunch of tools. I don't know, do people know they have these tools in their openCARP folder? So they're actually pretty useful things. So there's Igb head that prints your metadata about your data file. So I'll do some examples. It shows you what size your file is, what type of data. Hello, everyone hear me now? Yeah, so these tools are actually quite useful. So the Igb head is to examine just the metadata in a file, because there's a header at the top of the binary data in an Igb file. It's a very simple format. There's Igb ops, which lets you perform operations, simple mathematical or actually complex mathematical operations on an Igb file. So you don't have to waste your time writing MATLAB code, which people tend to do. I can do a lot of things in one line from the command line. Don't have to write a file. Igb extract to, it's not me, it's the projector. So Igb extract allows you to take out parts of an Igb file and convert it into text format for you. I think actually there are a bunch of different formats. Igb DFT, which will be there soon. There's a licensing issue with one of the libraries, but I think we're just going to open up the license on it. So then you can do a bunch of frequency domain operations. Most notably, be able to calculate phase and dominant frequency just with one command on the command line. And Igb APE, so it detects activations in your tissue as well as measures APE automatically over the whole tissue, and there's a bunch of parameters to determine exactly how you measure APE. So with that, why don't we go into examples. Okay, so here's an example. Okay, so I ran a simulation on. Okay, this is the way people often run Meshalyzer. They start Meshalyzer, and then here. I don't like to open up Meshalyzer. I like to put everything on the command line. So I ran a simple simulation beforehand. Okay, so it's a slab. It's a 2D slab. A couple things to notice right away when you do 2D slabs with Meshalyzer. If your model is 2D, which means that you have Z is 0 for all the points in your file, it will automatically assume that it's 2D. And when it assumes that it's 2D, it turns the lighting off. because lighting doesn't work so nicely in 2D, so you get a very washed out effect in 2D, so if you have even a flat surface, turn off the lights. The other thing it does is if you go into image, it automatically checks the no rotation button, because it's annoying when you accidentally move your mouse and you lose your plane, so that's it. We don't want that, so you can go reset transform and then make sure to turn off auto rotation. So, and oftentimes you'll see that the colors auto scale based upon the first frame of data, which is often at rest, so it takes the min and max as being minus 86.2, which means you're going to saturate the next frame, so I go a few frames and then recalibrate. And so then this is a simple simulation, just as simple as S1, S2, just showing you what we're looking at. So, and so by default there's 64 levels, but we can change the number of color levels. And we just do S1, S2, and we get our imagery. And we can change the color scale. This is this is called Turbo, which is a nicer version of the rainbow color scale, because you notice this version that your eyes drawn towards the yellow because it's not perceptually uniform. And there's nothing special about the yellow color, it's just that it's brighter and your eyes are drawn to it, but the red is actually a higher value, where with this one, the intensity should go with the, so it's meant to be more natural, or something like this color scale too. It's another perceptually uniform. But anyways, let's go to this one. Okay, so this is the data we want to look at. But then, for instance, say we wanted to look at the sodium channel activation. So the sodium channel has 3 gates, M, H, and J. And so the sodium channel is activated when the M, H, and J gates all go high. So how do we plot that on this? Well, I ran my simulations and I used a feature called G vector. So which is not the purpose here, but anyway, so if you're familiar with the G vector, the G vector feature of openCARP, you can specify this is the IMP. That's the ionic model used. I used the temperature 2. And the name, I wanted the M gate, so I called it M, and my output file I called M as well. So that's the M gate, and I also output the H gate, and I output the J gate. Then if you look at the file, so after the run, you can see I have an H, a J, and a small m. Why the m is not big, it's sort of because Apple isn't really 100% sure on how it treats capitalization. Apple is capitalization aware, but it sometimes recognizes uppercase and lowercase to be the same thing. But anyways, that's a detail. So anyway, so now I have M, H, and J. So I can go over here, and I could, for instance, I can load in my M gate. And this is the value of the variable M. You see it gets activated by voltage. So the dark blue is at rest, and it follows the M wave. If you look at another gate called H, H is the inactivation gate, which starts at high, and then it goes low as you get inactivated. So it's at resting level, it's high, and then as the voltage increases, it goes down. So it does the opposite. As M goes up, H goes down. And then H acts slower, so that's what gives you refractoriness. And likewise, if you look at J, J is an even slower version of H. So, but now we want to look at the sodium activation, which is when the product of M cubed H goes large. So how do we do that? Well, that's where IGB ops comes in. So if we look at IGB ops, and you can do minus H, and you'll see all the operations. You can do built-in operations. So there's 2 files. There's one file which you have to do, which is called the X file, and an additional second file called the Y file. So there's a bunch of operations. You can do AX plus BY, AX plus B. You can do point-wise division or multiplication. You can find the minimum over time at each point.
or you can find the minimum overall points at each time. And you can do that with the max, and you can do that with the average. You can do a running filter, you can do a box filter, you can join them time and space, center difference. You can normalize pixels, center deviations, and also if you have vector data, you can get the magnitude of data. And also, we can actually enter an arbitrary expression. So if you go this minus e, you can enter which I'm doing, because, and it uses, there's something called the mu parser. So, mu parser. It's a library, it's a fast parser library. So Igb ops uses this mu parser library, so it allows you to write arbitrary functions as, so you write these as functions of x and y. So for example, we have to get the product m cubed hj. So let's do our first operation is going to be m cubed. So in this, our input will be m, so we call that's our x variable, and we cube it. And we can do our output as m cubed, and we give it our, so all I said is evaluate the expression x cubed, because x is the first file, the Igb file that we input, and we're going to call our output m cubed.igb. And it's a fairly big data set, but it uses OpenMP, so it parallelizes the computation. And then if I look, I should see m3, so then I can load the data file m3. And all you're going to get is a thinner. Yeah, so it goes between 0 and 1. And you see, so m looks like that. Thank you. So now we want to do m cubed hj. So we could do, so for example, we want to do m cubed h. We can do x cubed times y, where, and we'll call this m cubed h, and we can go m and h. So x is m, so we do m cubed times y, and we call that. And so I hate intermediate files, so we'll try to do this in one command line. So of course now we're going to have to multiply by j, but I can only do 2 files at once. So we do some magic here. I put minus to make it the standard out. Then I pipe that, if you know Unix, minus e x times y. I say minus o, we'll call this excitation, Igb, and we put a dash telling it's from standard input, and we multiply by j. Okay, so go over this again. Everyone, is that too low on the screen? So multiply x cubed times y, where x is m, y is h. Output it to standard output. Pipe it, so pipe it to Igb ops, read from standard input for the x file, y file is j, and it's Igb. Oh, the second one. Wait for that to be done in 1 second. You know, so it's one. So there's. I'm looking at 1,000 data frames, so it's not always instantaneous, but okay. So m cubed hj, and excitation, and so you can see that, as you would expect, it just actually shows the wavefront. Effectively, that's where the sodium channels are firing. at the wavefront. So that thin line is the activated sodium channels. And waiting for the S2. Here's what I'm waiting for the second. There's the second shock, and then there's the wavefront of the spiral. And so we can see that it has a bunch of a rainbow colored effect, but what if we just wanted to actually threshold it, which is sometimes very useful. We just want to see the excitation front. So then we're actually, again, using the mean parser notation, we can just pick some arbitrary value, so say greater than 0.5. And so the final step here is when I just say use that equality sign. So if it's greater than 0.5, it's a value of 1. If it's less than 0.5, it's a value of 0. And
the threshold is low as.
not really.
Doesn't make a difference.
It makes a huge difference. I was playing with this last night. If you do 1, you get gaps in your. I did 0.01. Actually, no, yeah, point.
What are you doing 0.05?
Yeah.
Instead?
Oh, sorry. It should be points. Yeah. Wait, did I forget a 0? Anyway, so okay, done. So then one feature of Meshalyzer, if I want to reload my data file, I just hit the R button. And so you can see it's just a solid color. It's just the value of 1. So, and then likewise, for instance, say I wanted to look at the excitable gap. What would I do for the excitable gap? Then I would be looking at, I would just be looking at H and J. So when H and J are basically X times Y. Yeah, because sometimes people want to know the excitable gap. And we'll look where the excitable gap is greater, again, 0.05.
Should that be the file ending?
Pardon?
The output gap? Should that be gap.igb?
Oh, you're right. You are correct. It's a bit confusing because I'm inconsistent with programs, and sometimes I need an IGB. So move. Oh, good, we got that IGB. Maybe I'm smarter than I think sometimes. I think I might have coded it to make sure it always has an RGB extension. I don't know. I always think I was smarter yesterday than I am today. I say that every day and it's true, yeah. So here's the excitable gap. You can see as the excitation wavefront, it's all refractory behind, so it can't be excited. And then slowly we'll start to recover. And then you can see when the S2 is delivered, it was partly, and so now you can see the excitable gap. So that's, so you can see that's actually a very trivial thing to compute with these command line tools. And so yeah, those functions can be quite complex math functions. You can use cosines, powers, logs. So that offers up a lot of possibilities again.
Yeah, I assume you can script it all too. You can make like a post-processing script that runs all.
Exactly. Okay, so then also one thing people around here are interested in is phase. So how else can we calculate phase? So the first thing we do when you calculate phase is we, I'm not sure what I did. So to calculate, okay, so here's where I did my MQHJ, and then the first thing you want to do is you want a low-pass filter if you're going to do phase. And so IGB DFT lets you do a simple low-pass filter. So again, IGB DFT uses the FFTW3 library, which is very fast, and so I'm just high passing at 30 hertz because, and then I use the IGB DFT command operation called phase. So IGB DFT phase, and on my low pass filter, and I get an output called phase.
What was that parameter? Is there like 2000 or 2000?
So it says how many traces do you do in parallel, because it depends on the amount of memory your machine has. Because to do a DFT, you have to load the entire time series into memory. But it takes time to read a time series and then have to reset the file pointer back to the beginning to read the rest of them. So ideally, you just want to read all of them at once, but you might not have enough memory. So that n parameter tells you how many you can process at once. So you want that number to be as big as your machine can support. So what does the phase look like? So we look at the phase. Okay, so first thing about phase is I always like to have phase. I like to use a phase map that rolls over. So phase goes from minus pi to pi and then rolls over. And a lot of people, when you do this, you get a discontinuity because it makes minus pi and pi the same number. So if you go to the bottom of the color maps, you have a couple of cyclic color maps. This one, for example, you don't have that discontinuity at minus pi and pi, because the top of the scale equals the bottom of the scale. So you can so you have that version, you also have this version, and you look at that compared to this version. So if we're looking around here, you'll see a difference where you get an artificial discontinuity between the black and the dark red, which should not be there. And so this again, we'll get the fit. So yeah, for me to move the time slider, I'm holding shift. So if I drag it while I press the shift key, then it drags it over. If you click, it'll just go one time for you. So here's the recovery from S1. So what should phase look like ideally? The waveform in time. Anyone have an idea?
During a rotor or?
Yeah, during a rotor.
I don't know.
Right, but at one particular point, which should the phase look like? Anyone have an idea? It should,
Like a cycle.
it should look like a sawtooth. Like it should go up and down, this way, up, and then it should drop, up, drop, a perfect sawtooth. So you want to check how good your phase computation is. So let's pick a point. So we can pick a point again. To pick a point, you just pick vertex, and you click. And to see what the point is, you can control the picked point if you go up into the size of vertices. There's my picked point. And I click on the time series button. And so it's not a bad, and then ideally it should just be a straight line up, back, straight line up, but that's a pretty good approximation.
And is this really the case that it should be entirely linear? I don't think so.
Ideally. I think in an ideal world it should be. That would be the best.
Yeah. I guess if you had a rotor right in the middle of it.
Yeah, you can get perturbation, but if you're just simulating cyclically, it should be just linear up forever.
Should reflect the phase of the cycle you're in.
Yeah.
You want to move.
Yeah, if it's a constant cycle, it should be a triangle. Okay, so anyway, so this piece of so you just again here's picking, just pick P. There's different time series. You can, again, if people haven't seen, you press the hold button. That keeps that trace there, and then you can pick another point, and you can see it now. The old trace is in blue, and the new trace is in red. What was the one? Okay, so one more thing about phase that's a bit tricky. So people sometimes like to do contour lines with phase. So if we go to ISO surface and put on lines, and we go from to match colors. So when I press the match colors button, I think I showed this before. What it does is it copies the color scale onto the min and max for the ISO line values, including the number of colors there are, so that you get perfectly aligned color maps with ISO value lines. So if you want to do them randomly, just do, say, what's a good number? Say 12. Okay. So does anything look weird on this?
Why is there a thick one?
Why is there a thick one there?
Well, that's for the 2 meet, right?
Right, so he's right. So what happens at this thick line is that you have an edge of an element, and one is at minus pi, and one is at plus pi, and it does linear interpolation along the edge. So what's going to be, what's the average of minus pi and pi? 0. Which is erroneous.
Yeah, it's going to try and fit all of the lines that came into there.
Right, so, of course, I've encountered this once in my life. So if we go to data, under branch cut, and you say where the branch cut is, there's a branch cut at minus pi and pi, then it knows not to interpolate. And so, you have to watch that. I don't know if pair view does that, when you interpolate and so on. You have to be aware, explicitly aware that there's a branch cut there, to know not to let it mix up. Anyway, so that was the point I wanted to say. So the ISO lines again, I like ISO lines in 3D. Thicker, and I also like, and then sometimes I like to colorize them so they're the same color as. So it looks like an octopus in there. Okay. Same thing else I wanted to say about this. Okay, and then of course for the new people, this is, I like my view, so then I can save the state. I'll call this one. We'll call it just called phase. That's the name of the file. Then quit. Then I can just call up Meshalyzer. We're looking at our phase data, and where did I save it? Don't tell me I lost it. Did I lose it? I lost it. Oh, I see it. Okay. It's called a weird thing that we can order. So there it comes up with everything you saved, so you don't have to go through all that again. And then say we want to make a movie. So let's rename this thing to something. Okay, so now we want to make a movie. How do we make a movie without actually having to open up Meshalyzer? Go to H, and we can say minus, we give it a PNG file name, so we're going to call it phase. Say for now we're just going to do, say, 10 minus, what the number frame is going to be 10. The number frames you want to do, minus frame, we want to go into the first frame, so frame 0. I think that should do it. Exception to int. I just did this the other day. This is embarrassing.
Don't you need the equal sign? Sign.
No, it's
Anything else you're supposed to?
no, it doesn't. That you don't have to. It's optional. so there it worked. So we look at, so I created a directory called phase, and if we look in phase, you can see that we have two, why do we have two, only two, 10. So maybe this flag doesn't work. That's odd. It was working just a second ago.
But you named it differently.
Oh, did I name it A?
A.
Okay, there we go. Thank you. Thanks from the audience. You are useful sometimes. Okay. Okay, so now, I did A. So in A now you see all these PNGs. And so if you look into all the PNGs, these are all the different frames. So then now you can just take your favorite software and make a movie. So I use FFmpeg. I have my own little script called, so I can just not finding. Oh, because I started at 1 and not 0. And I can open. And there's the root. So that was just 100 frames. So it's very, very quick and simple to make. Once you have, once you set up the FFmpeg script, it's a pretty nice tool, and it's very well documented on the web. It's well supported on the web. You can do anything with it. You can make things faster. You can make things slower. You can filter. You can make crop images. So okay. So anyone have any questions about anything before we move on to the next?
The only thing that R reloads the RGB.
Yeah.
Oh, I didn't know that.
Yeah.
So when you run during the simulation, I always use the menu actually to reload. So use R if it frees it again. If there are frames being computed.
Yeah, you just press R.
Things that I didn't even know after 20 years.
All I can say, it's in the manual. It's been in the manual for 20 years. So. Okay, so where was it? Okay, so one of the things I added recently is Fresnel Shading. So this is clear objects. If you look through a piece of glass, like a thick piece of glass, you'll notice that the edges are dark, and that's because of what they call Fresnel Shading. It's based on that. So I did a cheap implementation of it. So let's see. So who's S62, Carly? S62.
Or the Singularities.
The most beautiful model that I've ever
No, we'll have to suffer through this model. So.
It's a gorgeous model that you can beat this.
You can't get better.
Well, I fixed it up a bit, you know.
There's nothing you can
So I like the -1 flag, and I always forget. So -1 makes everything one window. If not, you get 2 windows. So this is shows the effect. So this is a heart and lungs, and there's the hearts in many different places, different pieces. So the Fresnel shading is, so if you look, so this is the way it used to be drawn, so you don't see any of the edges. But anytime you have edges at the edge of a glass object, you get shading. And then this Fresnel controls the exponent of the shading. So the lower the value, the farther from the edge the effect is seen. So if I go high, you still see it, but it's at the very edge, a thin line at the edge. As I decrease the shading effect drops off slower with distance, so you get more of an effect. So you can choose the level that's just right for you. So then, yeah, and then surfaces, you can control all the surfaces individually. So yeah, you see the atria are solid, everything else is translucent. See, I've labeled, you notice all my surfaces are labeled, which you might want to take the time to do if you have complicated models. And it's very simple to label the surface. If you look into your surface file, again, you just all you do is add where you have a line that has the definition of tells you how many elements there are going to be in the next surface. After that, you just follow it with a surface name, and then Meshalyzer will put that name in, using it for the surface. So if you look at the next surface value, you see here, then it's RB, and then the next one is going to be RB fast. So it's very simple, just edit with a text file, or you can actually have Meshalyzer do that. You can highlight, if you highlight one. So when I check, like for instance, any operation is only done on any surfaces which are checked. So I can do LV, and then I can check rename, and I can rename the LV to whatever I want. And then by default, it will ask me to say if I want to save the surf file with the new label. So for example, say I want to shut off the torso, I click the torso, and I can do visible off. So there's two, you have to be careful that what visible means. Visible means that it can be drawn. It doesn't necessarily mean it's drawn, because I can be visible, but if I don't draw the solid or the mesh version of it, it won't be seen, but it's still visible. And which makes a difference for some operations. So, and then you'll notice here with lights too, what do I mean by back face? So when you draw, so all these surfaces, they're all composed of faces that are triangles. So the triangle has a front face or a back face. And it depends upon the order in which the three nodes are ordered that define the triangle. So when you see back face, means that the graphics card can detect all the faces which are pointing towards the back, away from the screen. And you can either not light them, you can light them, but then you can control the lighting. So if I then control torso fill color, that actually doesn't have much of an effect, because you can sort of see the effect. I'll show you a 2D example where that's better. Or culling, which means that don't draw anything in the back, which is fine if you have a closed surface. You don't need to draw the things that are facing the back, because the front ones will always. But it can make a difference when you're doing translucency. What you want is just what looks better. So it's darker, but if I take away everything that points to the back, there's less attenuation, because there's less things you're drawing, so it's lighter. Yeah, so for instance, yeah, and we can change, for instance, you can all invert to get rid of all of them. And then there's also a button here, so we'll turn a bunch of things off. And then there's the all, and then there's the shown button, which sometimes you get confused, and you just want to affect all the things that you see, so that the things that are visible, you click on the show button, and then all the visible surfaces are checked for. And then oh, I just did those ones, I turned those off, so I invert it, and then I can and then I can just all invert, and then for example the LA epi, you can then change the color to apply all. So if you can change the opacity, if you have a bunch of different objects selected, You can change the opacity without changing the color. If you press the apply all button, so this color and opacity and lighting selection will apply to all the surfaces that are checked. But if you only want to change the opacity, if you just click the opacity button, it changes the opacity or the translucency of all the objects, the surfaces that are checked, but it doesn't change the colors. But if you do apply all, that will also change the colors. So opacity means opacity. So LED Epi, we could change the color to pink. And to red, pink, and turn torso. And if you, and also, so there can also be a lot of information might be useful if you pick something. You can see I picked a point there. So there's another couple of features that are helpful. So if I picked a point and I want to look around that point, then I might want to hit this center vertex button, which then makes that picked point the center of the universe. So then all my rotations now are about at that point. So then I can zoom in on that picked point when I rotate it. Because if not, you're far from the center of rotation. You just go off.
How do you reset that?
Image, reset, transform. And it's back to where you were. Any questions? Okay. Okay. Let's get to. Let's go two.
If you have data on the different surfaces,
Yeah.
right? Is there just a single time slider, or can you slide it independently for each of them?
No, there's a global time.
Okay, and then it will expect data on every surface then?
It expects data on the points.
But on every point, then. So you have to have the data defined everywhere in order to fly through it?
Yeah, you have to have a placeholder for the data. If you don't have data, you have to have you can have a dummy piece of data.
Like zeros or something.
Yeah, and there's a feature called dead range. And then dead range, data, then lets you define not numbers, it ignores them, and then you can have a maximum and minimum valid data value. And then everything that doesn't fall within that range then gets colored with whatever color you say, or not, or opacity. So you can make it transparent, you can make it some gray, over gray that it's not on the color scale.
Right, but like if you wanted to, let's say you had data on the ventricles, but not, the lungs, you wanted to scale through it, then you have to define some sort of dummy data on the lungs.
Yeah.
But then you wouldn't need to show it as you're spending your time.
No. Okay. Exactly. So I've not yet covered every possible visualization piece. What's it?
You're all day.
Exactly. Visualizing fibers. I don't know if that's interested. Anyone interested in seeing fibers?
Yeah.
I think. So you can do fibers. It's a bit of a pain. We'll have to talk to Oral or Matthias to make it a bit simpler. Which one do you want So what do you think? One dev, go to your, yes. So, which you better see. Or actually, well, no, I'll just do 2D, which will be boring, but it'll go through the process. So, for instance, you know that the fiber information is stored in your .lon file, but you might want to see what it looks like. So it's a bit of a convoluted process, but I'll take you through it to try, and if you're interested. So the format of the lon file is very simple. It just has this is just the fiber at each point, what the fiber direction is. Sometimes there's a header at the top saying the number of fiber axes. Some people like it, some people don't. It's optional, and I get rid of it. So the first thing you need to do to display vector data, we first need a file with points at which to display the vector data. In this case, the fiber directions are stored at the center of each element, so then we need the coordinates of the centers of every element. So we can do that, but we first have to, we can use mesh tool, if people are familiar with mesh tool. And there's a command called interpolate node to element. And we need a mesh, we need some data defined on the nodes, and then we need an output file name. But it's sort of limited now, it only recognizes .vec files, so we link -s. All we have to do is change the extension, so we'll just call it fib.vec. Sorry. We need points first. So we have to copy our points file to, let's call it a.vec, because it only recognizes the vector format, and then it does not recognize points format. We just have to get rid of one line of the file. Now we can do mesh tool, interpolate node to elements minus where interpolar. Everyone's perfect when they're watching someone type, right? Minus slab minus I.dat. What did I just call it? A.vec minus O.dat. Points. And then if you look at slab dot center of points, those are the points that are the centers of every element. We just have to say how many there are. Control G, there's 160,000. So now we have the centers, and now we can interpolate now. We want to interpolate the what do I do? Okay, so now there's one more interpolation I have to do. So now I have the centers. Now I need to interpret the the what?
The files are on a final element centers. Now you want to put it on the nodes.
Now I have the slab. I have the points at the center of the elements.
Yeah, but
I need to transfer the nodes. No, what did I just transfer there?
Isn't it ready?
I got confused. This is confusing. I should have had this prepared. Is this? Yeah. Okay. What's A.vec? A.vec are the points, right?
yeah.
So now what do I want to do? Mesh to LM, interpolate.
So here you get the element centers.
Yes, and I have the element data.
Yes.
Right. So copy slab dot this E center. So we need again, we'll just B points, and we link -s slab dot one to E.vec. Now we're good.
Yeah, you just
And it's not going to be exciting because they're all pointing in the same way. So we can go to vectors, and if we say a fixed color, which is red, and with this dial we control their relative length. So that when we scale in, we see that
So dancing just right.
and stride, so we draw every 10th. And there you can see the arrows, and if we go stochastically, you can see the 5 direction. You can see the arrows. So there's just sort of one painful step there, well, a couple of painful steps, but you can, again, it's easy enough to do it for your 3D model, so you can see the 5 directions. And for some reason this is better in Linux. For some reason there's something funny on the Macs. I have to figure out why these arrows should be properly lit. They're not properly lit. And so that you can see the difference when what the stochastic button does. So if I do unstochastically, it just regularly samples every 10th vector. And then you can see how they all line up nicely because there's whatever it is, because the model every 10 points is a regular number of points. But if I do stochastically, it's random. And then there's the heads button. So then you can get a better idea. So you don't okay. And then what was the last one I wanted to, what else are we going to look at? Here's an auxiliary grid example. So for instance, one of the things people want to do is look at phase singularities. And just look at, well, I'll show you what it looks like first, and then we can look at the file format. Here's an example. See here, if we do back face culling, it doesn't work so well because it's a surface. And so you can see inside the hole, so everything facing back. So that's why culling doesn't work if you have open surfaces. So you can do, again, here's an example. Here we'll change the color of the light. So look at the back. So the backlight, if it's at 1, then the back and front are filled with the same. And you can't, it's harder to tell which is front and which is back. That's why I usually give a bit lower color on the back. And okay, and then so then there was a re-entry on this. So it should be a data file. Okay. So again, one thing to note here too, that's going to talk about this, is that in 3D, having a true black is not always the best thing, because true black doesn't show shading. Because all shading means less light. And if you're at black, you can't do less. So if I see something black, I don't know, is that because the data is black or just because it's in the shadow? So there's actually, again, this color map turbo, which tries to fix that by only going to dark blue, but not quite to black. So you can still get some shading effects on the dark blue. So this was the re-entry. And if you have a really long simulation and it's going too slow, at the bottom you see number of frames, and that tells you that controls how many frames it skips every time. So if I go 2, it's going to, or 3, I'm showing every third data frame. And if I want, I can even have it go backwards. But we'll go forwards. And then the difference between these two green buttons is one, the far right one with the two arrows loops indefinitely, and the other one just loops and goes until the end. Okay, so we have just a simple surface here. We have re-entry on the surface, and auxiliary grid, and we have auxiliary data, which are the singularities, the rotor code, the Wall Street. Scroll of course, maybe. So you can control it. You can control the color on the green ones. Why is that not another data point? Oh, there. And so so these actually are drawn as points. So they're actually the way I'm drawing these spheres now is they're not actually 3D spheres. I'm cheating, and so they can look okay, but sometimes they don't quite get the depth exactly right. So the other way you can render them is as true 3D spheres. So if I go from point to 3D, now I have to make them bigger to be seen. That is actually something drawn in 3D now. And when you draw, but I have to approximate it as a bunch of spheres. So the problem with drawing true spheres in 3D is that it takes a lot of triangles to draw a sphere smoothly. So I can't draw thousands of them because it just means but if you need the true 3D, if it really matters to you that much exactly how the sphere cuts the plane, then the true 3D is the way to do it. So you can sort of compare that one to what happens when I just draw these big points. No, that's really big. So the scaling is not, it doesn't preserve the scale in between. So I mean, it doesn't do a bad job, but it's not exact. But sometimes visualization is not about being exact, it's just being good enough. As long as it looks pretty, people will believe you. The prettier it looks. Okay, so yeah, that's. And then you can also put data. So besides position of points, the data is useful. I don't know what the data means here, but you can actually add data on each point, so the points can move in 3D as well as change color at the same time. So I think you have some different colors of data. Anyways, so those are basic singularities. So that's done as auxiliary data. And if you look at the auxiliary data file, there are three. So you have to make three files if you want auxiliary grids. So the basic one, you need a bunch of points at each instant in time. You can have an element definition at each instant in time, so you could have your own mesh at each instant in time that changes, and as well as data that's associated with each point as a function of time. So it's pretty flexible, but what you can display things auxiliary grids. And I think I have run out of time. So again, willing to get help from the community, people that are OpenGL experts. There's some few issues which I can help with. If you have OpenGL, alert to bugs. So if you can consistently reproduce a bug with a minimal data set, I can I can fix it very quickly. And I was like for feature requests and improvements. And as a final